independent events in probability. Two events are independent if the outcome of one event doesn't change the probability of getting the other event. We should write this very shortly, and I'll show you what I mean with this. So this can actually happen in two ways. We can be looking at two events in two ways. One is, of course, that we've got two separate experiments. Toss coin 1, toss coin 2. Draw a ball out of a bag, the first one, then draw the second one. And of course these can be with or without replacement. Now when I've tossed the first coin and got heads or tails, as we know really well, that doesn't actually affect the probability of getting heads or tails with the second coin. Whatever's come before doesn't actually cause any change in the probability. So when we're looking at two events or multiple events, one after the other, if they're happening with replacement, or if it's a scenario like dice or coins, then the first outcome doesn't affect the probability of future events, and so these are independent. The outcome of one event does not change the probability of obtaining the other event or the other outcome. That'll do. Now, comparing that to when we don't have replacement. So I've got, I believe, 1 red and 3 blue balls in a bag. And the probability when I draw out the first ball of getting a red is 1 out of 4. Now there was only 1 in there. It's not replaced, so that has changed the probability of the next outcomes. That's actually 0 out of 3 and 3 out of 3, which is 1. So I'm absolutely certain to get a, what did I say, blue ball this time, which is different to the probability before, because without replacement, it's changed the situation. If I'd got a black, let's say it's black, a black ball, that leaves 2 out of 3 remaining, and there's still 1 red remaining, but the probability's changed. So, if it's one event after the other, multiple experiments, with replacement, the events are independent. Their probabilities aren't affected by what happened before. Without replacement, these events are not independent. Now, mathematically, what we can say is that for independent events, the probability of A, excuse me a moment, sorry, just making a video. The probability, sorry people, I'm back. Probability of A isn't changed by what happens with B, so it will be the same as the probability of A given that B happened. So this rule, if this is the case, if the probability of A is equal to the probability of A given B, then the events are independent. And of course, for independent events probability, I have run out of space. Can also get the probability of both A and B happening by multiplying the probability of A by the probability of B. So just having a look at the tree diagram, for independent events, the probability of getting heads on the first one and heads on the second one is 1/2 times 1/2, which is 1/4. So we can multiply independent events to find the probability of getting them both. Now, let's just move up to there. We can also think of events being independent where it's one experiment, such as in this example, choosing a student at random, but multiple outcomes that we're looking at. My outcomes here are wearing a jumper and wearing a blazer. For these events to be independent, the same rule works. The probability of A would have to be the same as the probability of A given B. But when these events are independent, it means just because you are wearing a blazer doesn't mean you're any more or less likely to be wearing a jumper. So to solve these, we'll use a Venn diagram. So I'll run out of space here. Let's put this down here. We have students who are wearing a jumper, and that's 8 of them. Students who are wearing a blazer, that's 7. 2 are wearing both, and I know I've got 28 people here. So 8 minus 2 gives me 6 people wearing only a jumper and 5 people here wearing only a blazer. So people wearing neither. What have I got? 13, so I've got 15 people wearing neither. So the probability of A, oh, that's not very useful at all. I made them J and B. Jumper. Jumper given blazer. Well, that's useful. There we go. So probability of wearing a jumper is 8 out of 28. And of course we can simplify that one. 2 out of 7. The probability of wearing a jumper given that you're wearing a blazer means we're only taking it out of the blazer group, so it's out of 7. And how many people out of this group are also wearing a jumper? 2. Because those are the same, the probability of wearing a jumper is the same as the probability of wearing a jumper if we're wearing a blazer. That's saying that wearing a blazer hasn't affected the probability that you'll be wearing a jumper, so these events are independent. Now that's independent just for this scenario. If I surveyed another class who are wearing jumpers and blazers, I might find that you're more likely to be wearing a jumper if you're wearing a blazer, or less likely, something like that. But for this scenario, events J and B are independent. So you might want to learn how to do this with a Venn diagram. Sorry about the bell there. Less likely with the tree diagrams, but just remembering if it's with replacement, then our events are independent. If it's without replacement, they're not independent. This is our check for either of those, tree diagrams or Venn diagrams, as to whether events are independent. And remembering that if the events are independent, you can multiply their probabilities to find out the chance of getting both.